So now we were discussing your PN junction. So I discussed what is P type material and what is N type of material. Now let us see what happens when you join an P type material with a N type material. When you make a PN junction, what is the process happens? So you have a P type material. Okay, that will be a little bit more longer. So this is P section, and this side you have an N section. This is my P section, and this is my N section. Okay, and now you know how do you make a PN junction. Okay, you denote PN junction PP part by this type of impurity atom. These are donor atoms. These all are P type material. This side of section is a P type material. So say this is your P type material. And this side you have a N type of material. These are all impurities, acceptor impurities. These are acceptor impurities. Okay, so this is the junction, and now you know that all these atoms have electrons. Electrons, they are occupying electrons. So there is a high number of concentration of, and this side of section has a holes. Holes. I hope it's visible clearly. Okay, shall I make larger one, or it is it is understandable? Okay, so this is your P section, this side is your P section, this is your N section. Here you have a donor impurities which have an electron, here you have acceptor impurities which have a hole. Now because the concentration of electron is very high here and concentration of hole very high here, so whenever there is a concentration gradient, then a diffusion process happens. Okay, so what will happen, the electron this side of the the
सर
P,
पी और एन उल्टा बन गया सर.
P, P or
एन सर होल पी टाइप और एन टाइप.
हाँ, तो अच्छा मैंने उल्टा बना दिया.
हाँ सर.
ओ ओ just give me one, I make just that would make again. Oh, I have to make P type and N type ना. चलो दो लेयर ही बना देते हैं. So you have say this side you have P, so P means you have a this side, these type of atoms. Okay, so you have whole here. Okay, at this side you have N type material. Plus, 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 plus. Now, why do I am making this extensively so that you can understand what is the process happening? There is a P part and this is the N part. Okay, and here also you can make this same thing, but it understood. Okay, the same thing happens here. The same structure is here. Now, what happens when you have a you join together? Now you have a different sections of material. This side you have a donor impurity and this side is a acceptor impurities. Okay, Now what will happen? Because of concentration gradient, electron of this one, this side will move here. They will combine with this hole. Okay. So what will happen? These impurity will become ionized. These impurity will become ionized. So if I say up to this is ionized. This is ionized section. This is the ionized section, and this continues here. So this is the ionized section. So here what will happen? Here the region, here charge is present. Okay. So here some region is there where you have a charge distribution. One side is a plus, one side is a minus. So as charge will start moving, okay, more and more charges will appear in this section. So there will be a electric field will be produced. Now electron, because of diffusion, this is a diffusion process. Okay, so diffusion happening. This is a diffusion process. And now because of diffusion, you are getting more and more charge both side. And you know with the Poisson equation, whenever there is a charges, there will be electric field. Okay, so now because the charges are there, there will be electric field. Okay, tell me what is the direction of electric field? Electrons are moving here, so there will be a electric field. What will the direction of electric field? Tell me.
Sir, left to right.
Left to right. Okay, so electron is moving like this. Okay, and holes are moving like this. So a internal electric field will appear in the PN junction, and now because of this electric field, the force on the electron will be this side, and the force on the hole will be again this side. So what will happen at a particular steady state? This diffusion will stop. Okay, if this diffusion does not stop, then what will happen? If this diffusion does not stop, then these electrons will be keep on moving here, keep on moving here, keep on moving here. Okay, it will be keep on neutralizing this hole. So here all the section, all PN section will become charged. Okay, so it doesn't happen. So whenever electron moves, it combines the hole, and now charges are present. Slowly electric field develop, and in steady state, this electric field will stop further diffusion of charges. And now here, because there is a electric field, there is a potential difference. Okay, so here this side is higher potential, this side is a lower potential, and here in this side there is a no charges. In this is a neutral. This is a neutral PP region. This is a neutral region. These are neutral regions. So in neutral region, there is a no electric field. So electric field is only in the junction. Okay. And this junction width, I say if it is a 0, I say this is X, because this is N side, this is Xn, and this is a minus XP if it is a 0.
Sir,
So
why? Excuse me,
uh,
sir.
uh,
Sir, why these sides are neutral, sir?
because here the P section is already neutral, na? This is a P type, this is neutral. N type is neutral. Whenever we introduce an impurity, that is neutral. Impurity is always atom, na? Atom is neutral.
Okay,
So
okay, sir.
this section holes are not neutralized, or these electrons still are with these ions. Only where you making the junction, at the junction the electron is leaving the atom. Okay, so this part is neutral, this part is neutral. Only at the junction the charge is there, so electric field is at the junction. So if you see the potential is only potential this potential is high, and this side potential is low. This side potential is high, and this side potential is high. I'm only drawing the junction side, and this side the potential is low. So this is the potential profile. Okay, this is a Vn and this is the Vp. Now because of there is an electric field, this electric field is called built-in potential. Okay, so and a value of the built-in potential, because there is a voltage difference between here, this voltage potential is called built-in potential. And I'm not drawing the formula, I'm directly writing the formula is KTQ upon ln Na upon Nd Ni square. Okay, Na is what? K is a Boltzmann constant, 1.38 into 10 raised to power minus 23 joule per Kelvin. Okay, T is a temperature in Kelvin. Temperature in Kelvin. And Q is the electron charge. Q is electron charge. Okay, Na is the concentration of what? Concentration of impurity at which side? P side. Concentration of impurities, impurity atom, or concentration of holes. The concentration of impurity we say is equal to concentration of hole. So concentration of holes, we are assuming holes, or concentration of say impurity atom only. Okay, we'll see that one. Okay, impurity atoms at P side, and your Nd is the concentration of atom impurity at N side. And this is what? This is the intrinsic carrier concentration. If it is silicon, the value is different. If it is germanium, the value is different at room temperature. It is an intrinsic carrier concentration. Intrinsic carrier concentration. Okay. Now here already built-in potential is there, so you cannot flow current directly. Okay, you have to overcome this in internal electric field, then only you can overcome the you can flow the current in the PN junction. And now this VBI value depends on these factors. Okay, but generally when in electronics this VBI value is taken constant. We take V built-in potential. VBI is what? VBI is built-in potential. Built-in potential. This value is approximately, we take 0.7 volt, it could be 0.7, 0.8 up to 1 volt also. It can be more depending on the what type of junction is there. It can be 2, 3, anything it can be. Okay, but generally for we take 0.7 volt this voltage for silicon. Okay, and the same voltage we take as a 0.3 volt for germanium. Okay.
Excuse me, sir.
Tell me.
सर ये सर इलेक्ट्रॉन सर राइट टू लेफ्ट फ्लो हो रहा है ना सर, तो इसमें इलेक्ट्रिक फील्ड का डायरेक्शन सर किधर होगा जो
अरे
आपने
भाई, अब ये जो फ्लो हो रहा है वो तो डिफ्यूजन की वजह से फ्लो हो रहा है, इस इलेक्ट्रिक फील्ड की वजह से फ्लो नहीं हो रहा है.
अच्छा सर,
ओके,
उसकी वजह से सर कोई करंट इलेक्ट्रिक फील्ड नहीं होगा सर, जो इलेक्ट्रॉन सर इधर उधर जा रहा है.
फ्लो हो गया वो तो मोमेंटरी फ्लो होके वो डिफ्यूज हो गया.
अच्छा अच्छा.
वो तो डिफ्यूज होके न्यूट्रलाइज हो गया. ओके, और यहाँ पे चार्जेस प्रेजेंट हो गया, ये प्लस माइनस, इसके कारण जो चार्जेस इलेक्ट्रिक फील्ड होगा इस डायरेक्शन में होगा. जैसे जैसे एज सुन एज दे आर मूविंग they are producing charges, and because of the charges are left here, the electric field is increasing slowly, and the electric field is stopping the further diffusion. Okay, and this is the equilibrium condition where the no charge flow. This section is neutral, this section neutral, only electric field is in the inside the PN junction. Okay, now this PN junction, I want to flow current, or I want to use in the applications, so I will have to apply some bias. So this junction can be biased in two way. If I connect P of this junction with with P with plus and N is minus, this is called forward bias. This junction is called forward bias. And now this junction is only work as a diode. This junction is already make a PN junction diode. So now what will happen when I apply this? When I apply this positive here, negative here, what's supposed to happen? Tell me, what will happen?
Further diffusion starts
For that, why?
because of the applied bias.
Applied bias. So this electric field is stopping of diffusion of charges. Okay, and now I'm applying so first let us understand in electronic band diagram what happens before you apply this one. What happens in steady state when this junction is formed? So you have a barrier. You have a barrier of charges because there is a potential. Okay, what is the potential? I told you this type of this side is a plus, this side is a minus. This is a higher potential Vp, and this is a lower potential or minus potential Vn. And now if I multiply this potential with electron, that will become what? Energy levels. And because electron has a negative charge, so this potential will change like this. So this is the EC band gap, EC of P type material. Okay, and this is a valence band of N type P type material. Similarly, the band gap is same. So this is your EC of n-type material, and this is the EV of n-type material. So at the junction, this is the only band diagram of the junction. Okay, if I say isolated P and isolated P section, isolated N section, so this is your isolated P section, and this is your isolated N section. This is a P section, N section. They are exactly at same height. This is your ECP band diagram, EVP, this is ECN, and this is EEVN. Okay, they have the same band diagram. This is vanillus band, conduction band, valence band, conduction band, and this is your EG. But now what happens when you make the junction? Okay, in the junction there is an electric field. Okay, and wherever electric field is there, electric field is what? Can you write electric field like uh, d omega by dq? No. What is d omega by dq is what? What is the electric field? So electric field means,
It's
tell me what is it? What do you mean? Huh?
So it's a potential gradient.
Potential gradient. Very good. Potential gradient. So potential gradient. If I say EI is my potential, this di by dx electric field. Correct?
Yes,
Potential
sir.
potential energy gradient. dw potential energy gradient. So because here electric field is there, that means in this region there is a potential energy gradient. That's why this is the gradient. Okay, potential energy not constant. Potential energy curve has a gradient. That is the thing. That is why I'm trying to talk. Okay, so because the potential is there, because of movement of charges, there are potential charges. There is electric field. There is electric field means there is a potential energy gradient. So there is a potential energy gradient here. So this is PN junction in equilibrium. PN junction at equilibrium. And this potential energy gradient difference is your Q VBI. Q into VBI. Sign I already taken. I have already changed the sign this side. So this is your potential energy gradient. Okay. So now what? So this gradient means there is a electric field. Now when you bias this potential with a when you forward bias, what happens? Because of this battery, there is a external electric field. This is called external. It's called external electric field. Now, because of this external field will happen, this external field is against this field. So what will become? This barrier height will reduce. Now the barrier height will reduce. This is called forward bias. This gradient will electric field will reduce. So now this is your Q VBI minus V. How much voltage you're applying? V applied or V forward. This will be Q VBI minus V forward. So because of gradient, there is flow was stopped. Now because you have reduced the barrier height, again flow will start. Okay, and now current can easily move. Okay, electron can move because of this height is very small. This side you have electrons. This side in the conduction band, because it is an N type, you have a electron sitting here. I'm making little larger. This side, this electron is sitting, and here holes are sitting. And now some barrier is there, but they have some, because of temperature, they have some kinetic energy also. So these electron can move this one. Okay, electron cannot come from higher to lower side because it requires some energy. So if energy, they can now move. Okay, similarly, holes cannot slide, because when holes slide, their energy is increasing. So you require some energy to make them more down. So now these electron will start moving, and this electron will come here and then diffuse here and then recombine with the holes. Okay, and now current will start. That current is called diffusion current. So as long as V is applied, barrier will be keep on decreasing, and current, and now some current flowing. If you increase further Vm, what will happen? This will go more up, more less barrier, more current will flow, and if you have more current will flow. So as soon and for particular voltage, this barrier will completely reduce. So current will be keep on flowing very high with very higher exponential rate. So this is called diffusion current. Okay, this is a forward bias. Are you getting my point? And now next is what happens when you apply reverse bias. Now when you apply reverse bias, that means this is connected to negative, this is coming to positive, this is you apply reverse bias. Now the electric field will be, external electric field will be in this direction. And now what will happen? Instead of decreasing this width will increase. So this will become like this. This barrier height will increase like this. Okay, and now this QVBI, this become QVBI plus VR, because now you're applying in the direction of internal external field. So this barrier will increase. So once this barrier will increase, now what will happen? These electrons, these conduction electrons, okay, and here holes, they cannot move. They cannot, these electron cannot go here. Okay, these electron cannot go here. But what happens? There are some minority electrons present in the p section also. Okay, there are some minority, very less electrons are present here in the p section also. Now because of this high electric field, these electrons which are in p side, they are swept. So these are what here electrons are minority charge carrier, here holes are minority charge carrier. So this minority carrier charge are swept across the, because of high electric field here, these are pulled here, and they form the current. And now electrons are moving in this side, so current will flow in this direction. Okay, and this current is called reverse saturation current, and this is because of drift. Okay, so so two processes you have to understand, you have to keep in mind. Whenever you apply forward bias, the current which is flowing across the diode is called a diffusion current. Okay, there is a diffusion current, and this is in forward bias, diffusion current in forward, because of majority charge carriers, majority charge carriers flow. Okay, and this happened in the forward bias. Reverse bias, the current is drift current. The current is drift current. And this is because of minority charge carriers. Minority charge carriers. Okay. So that's thing I want to discuss. Now we can go to our PN junction. Is any student has a doubt? They can ask me, because this is very important. The things you should understand. Okay. One is diffusion current, which is happening because I am reducing the barrier width, and this current increases very fast. Other side, I have a very small current because of minority charge carriers. Here minority electrons are sweeping here and combining with the hole. So this current is very small, okay, because the number of minority charge carriers are very small. So this current is called a reverse saturation current. Now let me plot the IV characteristics of a PN junction. Okay. So IV characteristics of PN junction. And now all of you know what is IV characteristics of PN junction. If you measure the current I with respect to voltage, if voltage is positive, okay, this is your PN junction, which generally I represent by P section by triangle and N section by plate. Okay, now when you apply the forward bias, now because there is a built-in potential, okay, until you don't apply the forward bias equal to built-in potential, current will not start, diffusion current will not flow. So current will start flowing here, no current flow, and here, and then you apply, current will start. Okay, VBI, this is a variable, actually the variable little bit varying, but we can assume this is a constant. So this is varying, says it's starting from 0.7 volt for silicon. Okay, so and then current will exponentially increase. What happens in the negative side? If you apply negative side, there will be very small current will be flowing, very small current will be flowing, and at a particular negative voltage, which is called breakdown voltage, okay, suddenly current will start flowing. Breakdown means all the bonds in the junction will break down because you are applying so much high energy. Because of the energy, okay, this bonds will break, so all electron will become free, so this will become like a conductor. This will all suddenly current will start increasing, and the diode will get damaged, or p junction will get damaged. Okay, so there are two type of breakdowns. Okay, one is called avalanche breakdown. So breakdown, okay, one is called avalanche breakdown. avalanche Avalanche breakdown, and other type of called Zener breakdown. There are two mechanism via breakdown happens. Okay, now same thing, if it is a junction is a made of germanium, then this process will start with 0.3 volt. This is 0.3 volt, and this is 0.7 volt for silicon. Okay, breakdown voltage may be different, that we don't have to consider. So this is the built-in potential. Now this IV characteristics, okay, diode current can be approximated by this equation. This is called I naught or IS, reverse saturation current, exponentially Q VA applied upon eta KT minus 1. Okay, where eta is the constant, okay, K is a constant, T is a constant, V is the applied voltage, and eta is called, just give me ideality factor. Just let me know what is eta name. Eta is called ideality factor. Okay. So what is ID? ID is diode current. Okay. I naught is reverse saturation current. Reverse saturation current. VA is the applied voltage. Okay. K is the Boltzmann constant. Okay. T is the temperature. Now this equation also can be written like this. ID I know this is called diode equation. Diode equation or Shockley equation. Okay. Shockley equation. Shockley equations for diode PN junction. Shockley equation. I naught exponentially VA by VT minus 1, where VT is a thermal voltage, which is equal to KT by Q, thermal equivalent voltage, which we have seen for at temperature T. This value is, this is 225 or 26 milli electron volt. Now how to explain this curve with this equation? We can easily explain this diode with this equation. So let us understand what happens in the first forward bias. Okay. So when you start applying the forward bias, say I'm applying 0.7 volt. Okay. Now this is 0.7 volt. And what is the value of VT? Tell me, what is the value of VT at room temperature? What is the value of VT? 25 millivolt. Here is 0.7 volt. It is a 25 millivolt. Okay. 0.7 volt is 700, and this is 25. So this is the exponential value. This is very high. Okay, so say 25 divided by 700, how much will come? Approximately how much will come? Tell me how much will come approximately? More than 10? Yes or no? 700 divided by 25, how much will come? So very high. So this exponential is very high. So I can neglect this one compared to this term. So now the forward current, when you're applying forward bias, when your VA is V forward, my V applied is V forward, that time my ID will become exponential I naught, exponential Q VF by eta KT. Okay, you can neglect this one, and this is the exponential current flowing in the forward bias. Okay, now what has happened in the reverse bias? Reverse bias, again, this ratio is what? This ratio is very high, but this ratio is negative. Okay, in positive, this exponential is infinite or very high, and in the reverse bias, you have V applied is equal to minus VR. So what will happen? This this factor will become negligible compared to the is -1. So only the diode current will be equals to minus I naught. Okay, and I naught is the reverse saturation current. This is in microampere, generally in microampere. This is in milliampere. This current will be in milliamperes. So only very small current will be flowing in the reverse bias equal to the reverse saturation current, which is in the microampere, and the direction also opposite. Okay, direction also opposite because you are applying plus here, minus here. So always current this is the reverse bias. So here voltage here in forward bias, this is a positive, this is a negative. Plate is positive, plate is positive. Okay, P is positive. Here P is negative, and the current is flowing. This current will be always reverse saturation current value. This one. So this is a reverse saturation current. Reverse saturation current. Okay. So now we come to know two things from this IV curve. Forward bias, it is allowing the current, and reverse bias, this current is negligible. Okay. In the electric circuit, we consider this current is as a zero current. Okay. So we say in the whenever diode in the electric circuit, we say the current is flowing only in the forward bias, reverse bias. There is a no current flowing. Okay. There are some couple of more things I want to discuss here, but just I want to come directly to diode. Okay, because there is too much theories happening. So there, this reverse saturation current also is temperature dependent. This cutoff voltage is also temperature dependent. So you can remember that built-in potential. This is called also a cutoff voltage. Okay, so built-in potential is also called cutoff voltage. Cutoff voltage. Okay, decreases, that is VBI decreases with increase in temperature. This decreases with increase in temperature. Why? Because your VBI is basically KT upon Q ln Na upon Nd equals to Ni square. And as you increase the temperature, Ni increases, intrinsic carrier concentration increases. So you increase the temperature. Okay, increasing temperature, Ni increases. Ni increases, this makes VBI go down. So this same material, this VBI is function of temperature. Okay, similarly, this reverse saturation current also increases with increasing temperature. Reverse saturation current increases with increase in reverse saturation current increases with increase in temperature. Okay, so the dependence on reverse saturation current the temperature dependence of reverse saturation current is given by equation IO2 is equal to I naught 1 2 power T2 minus T1 by 10, and temperature is in Kelvin. Okay, what does this mean? Suppose you have some saturation current is flowing at temperature T1, and now you slowly increase the temperature T2, so this will increase. So if the difference is 10 degree, then IO2 will be double of I1. Okay, so let us say if T2 minus T1 of junction temperature is 10 Kelvin, difference is 10 Kelvin. In that case, what will happen? This I naught 2 will become 2 I naught 1. So the reverse saturation current doubles every time you increase the temperature by 10 Kelvin. Okay, so reverse saturation current doubles, okay, for every increase of 10 Kelvin, every increase of 10 Kelvin of temperature of PN junction. Similarly, built-in potential also depends on temperature. Okay, that we'll see some other time. And now let me discuss diode. So far, if you are in doubt, okay. So from here, what are the takeaway points? Takeaway points. Just I want to deal the diode. So for the takeaway points are there. The forward bias there will be huge current is flowing, and reverse bias there is no current. Diode cannot start until you apply 0.7 volt to 0.3 volt for silicon or some other voltage. Diode cannot start. That is a point number, takeaway number point 2. And then you should know about a reverse saturation current. Reverse saturation current is the temperature dependent. Okay, so these 3 or 4 takeaway points are there. Now let us go to the diode. Diode models. Okay, how to, like, you know how to treat resistor, okay, capacitor, inductor in the circuit, but how to deal diode in the circuit, because diode is the non-linear device. Okay, so say there are 3 models for diode. One is called ideal diode model. Ideal diode model, very easy. Third is constant voltage model. Constant voltage model. And the last is piecewise linear model. Piecewise linear model. Okay, now each of this model we'll discuss in detail. So first is your, say, ideal diode model. So what is ideal diode model? You can note down these models and we'll start one by one. Constant voltage model, piecewise linear model. Now what is ideal diode model? So ideal diode model says that this is your IV characteristics actual diode. Okay, this is actual. Ideal diode model says that this is not the actual. We will take approximate of this one. Approximate. So actual diode model says I don't require this cutoff voltage. I can start my voltage here itself without applying voltage. Uh, just drop in voltage is zero across. This is some voltage is there, okay, but that because voltage is very small, 0.7, for just for the approximation, I will take it as 0. So there is a 0 drop across the ideal diode. Okay, so ideal diode model says that number 1 point, diode has zero drop voltage. Okay, or the voltage drop across diode is 0. Voltage across ideal diode is 0. That means diode does not dissipate any power. The energy consumed by a diode is 0 because voltage is 0, but it can allow the current. Okay, current can flow through the diode on the circuit, depending on the circuit, and the current can go anything. So when this diode is forward bias, and a forward bias, you should understand, whenever diode is connected like this, this is the positive plate. So whenever positive plate is a potential, say VA, and negative potential negative as plate is, say V minus, say V plus, VP, and this is the VN. Whenever VP is greater than VN, I say diode is flow the current, and you can replace diode by zero drop in voltage. That means you can you can replace the diode with a short circuit. Okay, that means this is the I, this is the B, drop voltage is 0, but current can flow in the forward bias. This is the forward bias characteristics. This is a forward bias. And reverse bias, because this current is already negligible, I can take it 0. So this say the reverse bias current is, you're gonna keep on applying the voltage, but the voltage will keep on increasing, but current will be always 0. This is I 0. Here V applied 0, ID 0, and this is the VD. Here VD 0, VD drop. Here this voltage drop is 0. When voltage drop is 0, you can replace it by short circuit. And whenever you apply reverse bias means whenever this VP, VN, whenever VN is greater than VP, then you can replace this. This is a forward bias, and this is a reverse bias. You can replace, because no current is flowing, you can treat this as an open circuit. You can treat diode as an open circuit. Okay. So I am writing in the summarized form now. So this is actual model, actual IV characteristics, IV curve. This is ideal IV curve, ideal IV curve, or approximated IV curve for ideal diode IV curve. Now let me summarize this thing. So whenever diode is forward bias, okay, you have to find by seeing what is the forward bias. So in forward bias, diode will be replaced by a short circuit. Okay, and in reverse bias, this is a forward bias means this is higher, this is lower. Reverse bias, this diode will be approximated by a open circuit, short circuit, open circuit. Okay, here current is flowing, ID. Here current is ID is 0, but some VD is there. VD will be measured like, so VD always you measure plus 2 minus, okay, but here VD will be negative. So this is, you always measure VD like this. So here if you want to measure VD will come out negative. Okay, VD is negative. Here VD is negative, and here VD is 0. Voltage drop across this VD is 0, but ID is flowing. Okay, let us understand this model with some questions. Can I erase this one? Deepak, Akansha,
Yes, sir.
Sarvanti, Yoshita, are you
Yes,
getting?
sir.
You're getting what I'm saying here?
Yes, sir.
Okay. Now let us understand the problems. With problems, every concept will be clear. Okay. So the number one question is that you have a say a battery of 5 volt. This is my diode. Say this is a 1 kilo ohm resistor. Okay, and this is the ideal diode. In the question it is given this is the ideal diode. Okay, find the voltage and find the VD. VD will always this one. Find the voltage difference VD. Okay, and this is your 5 volt. So whenever diode in the circuit, first thing is there, you should know what is the applied voltage. VD is positive or negative. Tell me VD is positive or negative. Tell me in the question. VD is positive or negative?
Sir, positive.
Positive. See, how do you measure VD? This voltage, suppose this is a 5 volt, this is a 5 volt, this is how much? So whether to find whether it's a positive or negative, you just have to just make it open. Okay. Now once you make it open, obviously this point is 5 volt. Whether diode is a forward bias and reverse bias, for that you have to always make it open terminal to check the voltage difference. यहाँ पे voltage कितना है? Here voltage. So this potential is 5 volt. Okay, here no current is flowing, and this point is battery. This is basically grounded. So this is also grounded. So no drop is there. So this is also grounded. So this is 0. So we can say the diode is forward bias. So this is 0. This point is 0. 0 volt is 5 volt. Diode is forward bias. So I can say what? I can say this diode is forward bias, and an ideal diode whenever forward bias you can replace by a short circuit. Okay. So the question is find VD and V naught. Tell me what is VD and V naught in the question. So this will be replaced by a short circuit. But tell me what is VD and V naught here. कितना आएगा? What is the value of VD?
So 5 volt.
VD and V naught.
सर इक्वल VD इक्वल्स टू V नॉट 5 वोल्ट ही हो जाएगा सर.
कैसे हो जाएगा बताओ? VD कितना होगा हमेशा डायोड में, आइडियल डायोड में? What is voltage drop, Tamanna? What is voltage drop across diode? आइडियल डायोड मॉडल में क्या होता है?
Zero.
Zero. Short circuit is there ना? Just for checking, we have seen how much difference is coming. VD always measured when you keep the diode in circuit. Before that is open circuit voltage. If open circuit voltage of these two terminals is greater than 0, that is forward bias. So once forward bias, now if you connect the diode, this will take a 0 drop, no dissipation of power. So this becomes 0. So because this 0, this voltage will directly come here. So your V naught will be what? 5 volt. Okay, if you want to measure what is the ID flowing through the diode. So ID in the circuit will be, tell me what is the ID? ID will be 5 volt divided by 1 kilo ohm total resistance. That is 5 milliampere. So ID flowing 5. So drop is 0, but current is 5 milliampere. This is ideal diode. That is simple. Just find out whether it is a forward bias or reverse bias, and you can solve the problem. Okay. Let me do some more small problems. Then you will understand how to solve this one. Say now let me put it same circuit. I say this is my 5 volt. Okay, and here you have a diode. diode, and now I'm putting resistor here. I'm putting diode here. Okay, this is 1 kilo ohm. Okay, now tell me what is ID, and I am measuring the V naught here. V naught will be basically VD only. So say this is VD. I am measuring VD equals to V naught. I am measuring here. Okay, so V naught. What is the V naught here, and what is VR here, and what is ID in the circuit? Tell me very easily. What is the value? What is VD? What is V naught? What is VR? So first thing is you have to find whether this, if you make it open, whether it is a forward bias or reverse bias. What is open circuit voltage? Salavanti, is a forward bias or reverse bias?
Sir, forward bias.
Forward bias. If it is forward bias, then the voltage across this will be VD will be how much? So find VD, V naught, VR, ID. So here this is VD. VD is
VD
always
is
equal to
0.
V naught. So this is 0 volt. VR will be how much? So
5
here
volt.
0 volt here is, the remaining will come here. This is the 5 volt. And ID will be how much? Same 5 upon 1
5
kilo, 5,
milliampere.
5 milliampere. That's it. Now let me modify this circuit little bit more. If this circuit is there, plus minus 5 volt, okay, say this is R, 1 kilo ohm, and here say my diode is there, and here some battery is there of 1 volt. Okay, I want to say, tell me what is V naught, what is VD, okay, and what is VR. Tell me. Tell me, diode is forward bias or reverse bias? If I make it open, if I make this terminal open, so what will become? If I make this terminal open,
It's forward biased.
so this is a 5 volt, this is a 5 volt, and this is minus 1 volt. So total volt VD is 5 minus 1, it's still 6 volt. So this is the forward bias. So forward bias is there. That means I can, so you have to find V naught, ID, VR, everything. Okay. So this is short circuit. This is short circuit. Okay. So tell me what is V naught? What is V naught in the circuit? How much is V naught? This is V naught. This is 0 volt. This is V naught. So V naught will be minus 1 volt, because this is the parallel. This is the minus 1 volt. Okay. Now I want to measure what is VR. So I can write KVL, apply KVL here, minus 5 plus I into 1 kilo ohm, okay, minus 1 volt equals to 0. So my I into 10 will come, is minus 6. So my I will come 6 upon kilo ohm, that is 6 milliampere. and if the 6 milliampere, okay, my VR is I into R, that is 6 milliamps into R is 1 kilo ohm. So this become 6 volts. So all the voltage is coming across this resistor, this one and this one. Is that point clear to everyone?
Yes, sir.
Yes,
Yes,
sir.
sir.
थोड़ा सा और I'll modify a little bit more so that this thing should be clear to you. So I can go the actual problems. Before that, you should first learn whether it is a forward bias or reverse bias. Same diode I'm putting here, and now I'm putting here a battery of 2 volt. Tell me, find V naught, VD, ID, and R. Okay, ID. Tell me what is V naught. Tell me, this is a forward bias or reverse bias? It is a forward bias or reverse bias?
So forward bias.
Forward bias, because you have a diode. This is that if you make it open, then this point is 5 volt and this point is 2 volt. So this is a plus 5 volt, this is a plus 2 volt if you make it open. When you open only, then only. Okay. So this is a forward bias. So when it is a forward bias, now you can replace it by a short circuit. Okay. And now V naught will be directly this voltage 2 volt, and now you can apply KVL in this equation. VD will be of course 0. Ideal diode is given. Okay, ideal diode model we are doing. VD is 0, and you can write the KVL minus 5 plus VR. VR is ID, because the same current ID is flowing. ID into 1 kilo ohm, and now this is plus 2 volt equals to 0. So ID into 10 raised to power 3 will come minus 5 plus to minus plus 3. So ID will be your 3 milliamps or 3 amperes, and VR will be 3 milliampere into 1 kilo ohm. So that will be 3 volt. VR will be 3 volts. So if you understand all the little things, let us understand the reverse bias now. Shweta, are you getting this one?
Yes, sir.
So let us say now you have a, say again, this is a 5 volt battery. I am putting a diode here. This is a resistance R, 1 kilo ohm. V naught. Okay. VD will be always measure with respect to here. VD will be always measure like this. Okay. Tell me, find V naught, VD, VR. बताओ कैसे निकालेंगे? Diode is forward bias or reverse bias when you make it open?
So reverse
Always.
biased.
Okay, always check with open terminals. So this is a reverse bias. Is there any student who is still not getting forward bias or reverse bias? Tell me. I will repeat again. So this diode is reverse bias. So whenever reverse bias, ideal diode, this is open. You can treat it as an open circuit. Okay. When open circuit. So what is the value of ID here? What is ID? ID will always flow like this because voltage is like this. What is ID?
0.
5
जी-
milliamp.
5 मिलियन कैसे? करंट ओपन है ना, करंट तो फ्लो होगा ही नहीं, ID 0 हो जाएगा. What is VR? V naught. What is V naught?
5
हाँ,
5 वोल्ट सर.
इसमें कितना करंट है?
सर 5 मिली एम्पियर.
करंट कितना है इसमें? 5 मिली एम्पियर. कैसे करंट? करंट ये तो जीरो है ना,
हाँ
ओपन है ना,
करंट सर.
करंट जीरो है.
यस
तो
सर
V naught
करंट जीरो.
तो V naught कितना होगा? करंट जीरो तो V naught कितना होगा? V naught तो ये वोल्टेज है ना, कितना होगा?
सर जीरो हो जाएगा.
0.
जीरो हो गया. Voltage will be zero. Okay. If the current is zero, open circuit, no current flowing, this V naught is zero. VD कितना होगा? What is VD?
ये 5 वोल्ट होगा सर.
5 volt होगा,
-5.
Minus 5 volt.
माइनस 5
5
वोल्ट.
So you can say this is VD. So you can apply KVL here. Minus VD. So minus 5 minus VD. This is minus VD. Okay. Plus to minus always measure. And this is plus V naught equals to 0. V naught is 0. So your V naught is 0. So minus 5 minus VD. This is 0, 0. So VD will be minus 5 volt. So all the voltage is coming across the diode in reverse bias. I think you have understood now. Just I will give one more so that these things should be clear. This is 5 volt. This is the diode, a 1 kilo ohm resistor. I am measuring V naught here. Okay. VD is this one. This is R. Okay. This is a VR. Tell me. Say this current is I. Find I in the circuit. Find V naught, VD, VR, and I in the circuit. Diode is forward bias or reverse bias? Diode is forward bias or reverse bias? Leo,
So रिवर वाइज.
reverse bias. Reverse bias means we have to make it open.
यस सर.
Make it open. Now what is current flowing in the circuit? What is current flowing in the circuit?
So 0.
0. What is VR? What is VR? What is VR?
5 volt.
Are there current? Is there any current in the resistor? Is there?
No sir.
Then why VR will be 5 volt? If there is no current, VR will be 0. Okay. What is V naught? Tell me V naught. What is V naught?
Not 5 वोल्ट.
So no drop. So this is the 5 volt. No drop here. So this 5 volt is coming here. So V naught will be plus 5 naught. What is VD? What is VD?
minus 5 volt.
Minus 5 volt. VD is minus V naught. Here measuring like this. This is opposite of this one. VD is minus 5 volt. Okay. So just small thing you understood. Everything, every subject you have to understand small things only. When you do small things correctly, everything will become clear. Everything will become right. It's not a big thing you have to understand. Okay. You just have to understand the concepts. So now you are ready. Tell me. Is there any doubt? Okay. Now let us solve. I have a 9 volt battery Okay, you have a 600, say 600 ohm resistance, 300 ohm resistance. Okay, and now you have a diode, and you have a 100 ohm resistor. Okay, tell me how much ID is flowing through the diode. Okay, so this type of questions can be done in many ways, but I want you should follow always single method. Okay, so this, if I make it this diode open, so this diode is a forward bias or reverse bias? Tell me.
Sir, forward bias.
This diode is a basically forward bias. Okay, how? If I make it open, okay, if I make it open, and then I see here no current is flowing, so this point is 0, this point is ground, this point is ground, this point is 0 volt, and here some voltage is there, some drop will be here, there's some voltage is there, some positive voltage will be here. Okay, so 9 volt is dividing, getting 900 ohms, so here will be 3 volt, and 3 volt will make it positive, so immediately you can replace it by short circuit, and now you can solve the circuit and you can find the current value. That's the easiest, this is the way. Okay, but this is simple circuit. In the future time we may have a little bit tougher circuits, so the best method to solve diode circuit is there, you use Thevenin equivalent model. Okay, because Thevenin equivalent circuit will make every circuit in the single loop. Okay, so what is the way of making Thevenin equivalent? So in order to make a Thevenin equivalent, you can solve like this also, and the answer will come. You find a total resistor, you find the current I, and then you apply some current here, some current here, that will be your ID. You can apply current division, you can find the current, and that will become, let us calculate first this way. So now the total resistance will be how much? Total resistance R equivalent will be how much? This is 600 ohm plus this 3 and this is on parallel, 3 and 100 divided by 400. Okay, this is how much? This is 75. So this become 675. This is the R equivalent. The total I in the circuit will be how much? I will be in the circuit, this I, 9 volt divided by 675 ohm. Okay, so this will be how much? 3, if I do 2, 2, 5. Okay, just check the calculations. Is correct or not? 2, 2 to 5. Okay, this is current. This is total current. And now I want a current ID. So ID, I can apply current division. Say some current is flowing here, ID is flowing here. If I want a current in this branch, I will take total current, that is 225. Okay. The opposite branch has a 300 ohm resistance. Okay. And sum of resistance 100 and 300, that is 400. So if you solve this one, how much will come? Tell me. How much will come? How much current will come? Tell me. Tell me how much current will come. What is the ID is coming? Just check this calculation first. This is 675. This is correct. 6 upon 675. 1 by 75. Okay, 1 by 75. Correct. So this is basically 1 by, this is equal to what? 1 by 75. Na? 7, 1 by 75. Okay. So you can use, this is 1 by 75 and 300 divided by 400. Okay. So how much will come? Tell me. 3 upon 300. 1 upon 100, that is 0.01 ampere, that is 100 milliampere. Is that correct? Karishma?
Yes,
No
sir.
one is- Okay.
Yes, sir.
Yes, sir.
Okay. So now this is the one method. You can use any method. whatever you find easy, but I want to tell you one more method. Okay. Now I will use always this method. So first of all, what I'll do, I don't know whether my diode is forward bias or reverse bias. So what I will do, I'll make always Thevenin equivalent circuit. I'll make it open here. Okay. Now I will find what is the voltage here, V Thevenin, V open, and R Thevenin. Okay, across this open circuit. So what is V Thevenin? Tell me. V Thevenin equal to V open. How much is there? So obviously here this will be V open will be this voltage minus this voltage. This voltage is already 0. So I have to find what is the voltage here. So current is always flowing here. So I can say my V Thevenin will be V open will be voltage across here. This is my V Thevenin basically. This is my V Thevenin. So V Thevenin will be 9 upon 900 into 300. Okay, that will be how much? 3 volts. 3 volts. Okay, and what is R Thevenin? R Thevenin across this resistor. So I have to make it short. So R Thevenin across this one. This will be in parallel. So R Thevenin will be 300 parallel to 600 plus 100. So this is 300 into 300 into 600 upon 900 plus 100. This is how much? Tell me. This will be 1800
300.
upon 9 plus 100. That will be 300, 200. That will be 300 ohms. Okay. Now the equivalent circuit will become plus 3 volt and R Thevenin is 300 ohm. And now I am putting back my diode as it is here. So this is my final circuit, and now I can find what is ID flowing through the diode. Same way, okay? So the diode is forward bias. I can treat it as a short circuit. Okay. The current ID will be simply ID will be 3 volt divided by 300. Answer is same 0.01 ampere or 100 milliampere. The way is same, but always try to do problems like this. That will become the things easy. Okay. So let us stop here. We know how to now find how whether diode is forward bias or reverse bias. Tomorrow we learn more about how to deal the problems. Okay, thank you. I'll stop here. Thank you.
सर
Thank you, sir.
Thank you, sir.
हाँ बोलिए.
सर ID is 10 milliampere.
10 milliampere. Yes, 10 milliampere. Yes, 1 by 100. Na? 10 milliampere. Correct here also. Calculation here you can. Okay.